All right. So, in this lesson, we are going to learn about, or hopefully review, balancing equations and stoichiometry. So, welcome to asynchronous AP Chemistry, and I hope you're ready to go. So, in order to get to stoichiometry, we have to talk about balancing equations first. And as you remember from first year chemistry, in order to balance equations, or the reason for balancing equations, the concept is that the mass must be conserved in all reactions. Conservation of mass is a very important concept. So we're going to balance equations so that we have the same number of each type of atom on both sides of an equation. And that's what we're going to be aiming for. One of the things that I like to tell people is basically we're going to be increasing the coefficients in the reaction until we have the correct number achieved, rather than trying to decrease or go the other way. It's a little bit easier. So in our first equation, where we got nitrogen and hydrogen reacting to form ammonia, one of the easiest things to do is to notice that we've got even numbers of nitrogen and hydrogen atoms on both sides, and an odd number of nitrogen and hydrogen on the right. And so we're going to need to make that even. So the best way to make that even is to just put a 2 in front here. So we want to make nitrogen and hydrogen even. And when we do that, now we have a total of 6 hydrogens on the right. So we need 3 hydrogen molecules to make 6 hydrogen atoms, and we need 1. And there's an implied 1. You don't need to put that 1 there if you don't want to. Blank, no coefficient, will be read as an implied 1. In this next equation, we have oxygen in 3 places, two places in the products and 1 in the reactants. So we're going to leave it to last because we can basically put any coefficient in the in front of oxygen, in front of O2 to make it work. So I usually like to start with the most complicated or most complex formula in the reaction, just because once I get those elements balanced, everything else should fall into place. So I start off with 6 carbons on the left, and that means I want to have 6 carbons on the right. Let's come back to and revisit the oxygen in a moment. We have 6 hydrogen atoms on the left. To get 6 hydrogen atoms on the right, I need 3 water molecules. And now I've got a total of 12 plus 3 is 15 oxygen atoms on the right. In order to get 15 oxygen atoms on the left, I can put 15 halves, 7.5 there. If you want to leave that as 15 halves, you can. Some people prefer to double everything. So if we double everything, don't forget the implied 1 in front of the C6H6. So we'd have a 2 and a 15 and a 12 and a 6. And that should also balance. Good practice is to go through and make sure that you have everything balanced out. In number 1, it wasn't so important because it was pretty straightforward. In number 2, let's go through. With our doubling, we have 12 carbons on the left. We have 12 carbons on the right. We have 12 hydrogens. We have 6 times 2 is 12 hydrogens. We got 15 times 2 is 30 oxygens. 12 times 2 is 24, plus 6 is 30 oxygens. And so we're all balanced. In number 3, we have the same situation we had in number 1, where we're going to start with, this is ethanol. We're going to start with the ethanol, but we have to notice that there is 1 oxygen already in the left in the ethanol. So that's going to add a little complication to our balancing. So let's start off 2 carbons on the left, 2 carbon dioxides, 6 hydrogens. Don't forget to add those together. So I need 3 water molecules. So now I've got 4 plus 3, I've got 7 oxygen atoms on the right. And so what I need is 7 oxygen atoms on the left, but I already have 1 here. So if I have the 1 plus something to give me 7, don't forget that that 1 is already there. So that something is going to be 6, and 6 divided by 2 gives me 3 oxygen atoms. And that gets me balanced on the right. So the half coefficients are okay for diatomic elements, but notice or be aware that when you get to the AP test, especially in the multiple choice, but sometimes in the FRQ too, they'll ask you what's the smallest whole number coefficient that you put in front of an atom or in front of a substance. And so you want to make sure that you know how to get to that whole number coefficient. And number 4, we're going to have a little extra to do where we have to actually come up with the formulas of the materials before we go through with the balancing. And so take a moment. You can pause the video for a moment and then come back, and after you've filled in the formulas, come back and let's check your work on that. So lead 2 sulfate, lead is Pb, sulfate is SO4, and lead is a 2 plus, sulfate is a 2 minus, so that balances out. Let's leave a blank. We don't have to worry about the states right now. Sodium phosphate, sodium is Na, phosphate is PO4 with a 3 minus charge, so we need 3 sodiums to go with that. We're going to make lead 2 phosphate, so lead 2 phosphate, Pb, and PO4. So the lead is a 2 plus, phosphate is a 3 minus, so we need 3 Pbs, and we need 2 phosphates. Let's just put the charges in. Let's do it in a different color. I'll go back and do it in a different color. And sodium sulfate, Na2SO4. So just in case you are struggling with the charges, we got a 2 plus and a 2 minus. We've got a 1 plus and a 3 minus. We've got a 2 plus and a 3 minus and a 1 plus and a 2 minus. And so that's why we get those subscripts the way they are. Now, what we can do is we have several polyatomic ions in there. If we tried to balance all the oxygens, we got oxygen in all 4 of our substances. If we tried to balance those oxygens, we would get into some severe weeds, and we don't want to do that. So what we're going to recognize is that the polyatomic ions are not changing. They stay intact. Now, we are going to run into reactions where the polyatomic ions are going to decompose or they're going to get formed. You can't do this in that case. But now we can notice that we have balancing, polyatomic ions can be balanced individual as a whole, as a group. Also, it's good to balance out the elements that have an even number on one side and an odd number on the other. And again, I want to start with the Pb, with the lead 2 sulfate, because lead 2 phosphate, because it has the most complicated coefficients. Now, it does say an even number, an odd number. You can try to balance out the sodiums. That might work. But I think the easiest thing to do is to start with the lead. So we've got 3 lead. Let's put a 3 in front of the lead sulfate, lead 2 sulfate. We need 2 phosphates. So if I put a 2 in front of the phosphates, now I've got 3 lead and 2 phosphates balance out. I've got a total now of 3 sulfates on the left, and I've got a total of 6 sodiums. And so if I put a 3 in front of the sodium sulfate, that balances out, and we are done. So for mercury 2 oxide, and we heat it, and we're going to make mercury plus oxygen. Again, pause the video for a moment and come up with the formulas and the equation, and then we'll come back. All right, so mercury 2 oxide, mercury Hg, oxide is O. We have a 2 plus and a 2 minus, so that balances out. The arrow heat is indicated by the delta over the equation, or you can write heat. And we're going to make mercury metal and O2 gas. Don't forget about your 7 diatomic elements, the Hofbrinkels, as we sometimes call them, or Brinkelhofs, I think some teachers call them. The 7 diatomic elements. A little balancing. We need 2 oxygens on the left, so we need 2 mercuries on the right. That was a nice, easy one. And number 6 is going to be a complicated one. There's going to be a related, similar equation in the homework, but instead of having NO2 in the product, it's going to have NO in the product. And so it's going to give you a slightly different balancing. So this one is a little complicated because we've got elements that appear all over the place. Multiple species. On one side, we got oxygen in 3 things on the right. We've got nitrogen in 2 species on the right. And this is one of those cases where the NO3 is actually breaking down. So you can't balance the NO3, the nitrate, as a whole. So how do you start something like this? So the way you're going to start something like this is you're going to notice that in this case, we have an even number or multiple of some number of specific atoms on the right. What that is, we have an even number of hydrogens because we have water, H2O, and we are going to end up with, if there's an even number of hydrogens on the right, that means there must be an even number of hydrogens on the left, and so that forces us to give an even number of nitrogen atoms as well, which means the coefficient in front of the nitric acid and the coefficient in front of the NO2 have to be even in the end. So we'll get to that. Now, the coefficient in front, the last thing that that's going to do, now that's also going to give us an even number of oxygens. So we're forced, that even number is being forced on us by the fact that we've got the H2O in the right. And so the coefficients in front of HNO2 and HNO3, NO2, and water are going to be even. So when you come up to something like this, the best thing you do is increase the coefficient on the HNO3 one at a time. Why? Because that's going to give you the ability to check. You'll check after each iteration. You might have to go through a little iteration, trial and error here. So right now we have that implied 1 in front of here, and that implied 1 doesn't work because it's not even. So 1, it says 1 number at a time, 1 even number at a time. So let's put a 2 in front of the HNO3, and what's that going to do for us? That's going to give us 1 water, and it's going to, that doesn't work. Why doesn't that work? Because we have 2 nitrogens on the left, but we have 3 nitrogens on the right. So we cannot balance this with just 2 nitrogens on the left. So the last thing is we need greater than 3 nitrogens on the left in order to get even numbers. So the 2 didn't work. Let's go another even number. So I'll leave my work there and you go in a different color just so you can see how this process is working. So if I change that to a 4, so now I've got 4 nitrogens. And what that's going to give me on the right. So 4 nitrogens, 4 nitric acids. I'm going to need 2 water molecules. So that's going to give me 4 hydrogens. That's good. I've got 4 nitrogens and 4 hydrogens. Now I get to split between, I can decide between where I'm going to put the NO3, if I'm going to put a 2 in front of the copper 2 nitrate or a 2 in front of the nitrogen dioxide. Because I need an even number, actually, if I put a 2 in front of the copper 2 nitrate, that doesn't work. So I'll put a 2 in front of the nitrogen dioxide here. So that's going to give me now a total of, if I add them up, 4 nitrogens. Okay, so far so good. I've got 4 nitrogens, 4 hydrogens. Now let's check our oxygens. I've got 12 oxygens on the left. Let's see what I've got on the right. I've got 6 oxygens plus 4 oxygens plus 2 oxygens. 4 plus 6 is 10 plus 2. I've got 12 oxygens, and this is now balanced. If you need to go much past this, going up to 6 nitric acids or going up to 8 nitric acids, I wouldn't go much farther than that just because it's unlikely that you're going to have such high coefficients in the balancing. We will see high coefficients later on in the year in balancing redox reactions, but let's not worry about that right now. Okay, so we noticed again the HNO3 must have an even coefficient, and point up to here for our discussion of why. All right, so that's basically it for balancing. All other problems are going to really be a lot simpler than number 6. And number 6 is probably the most complicated one, and the one that's in the homework that's based on it that you will see. So let's then turn our attention to basic stoichiometry. So if you remember, the concept of stoichiometry is that the coefficients of the balanced chemical equation, and we're going to have a balanced equation, are going to become mole ratios, B over A, where B is what we're looking for, A is what we're given. So the mole ratio of B over A to get from the moles of the given to the moles of whatever you want. Now, B and A can be in any place in the reaction. They can both be reactants, they can both be products, or one can be a product, one can be a reactant. And we're just comparing the amounts of different substances, the moles of different substances in the balanced chemical equation. Also, you notice on this flow chart that you won't always be given moles as a starting or ending spot. So you will have to do some conversions. You can be given the mass, you could be given a volume, and this volume could be a solid, liquid, or a gas, and be given the density of the material, convert to mass. You can be given a gas at this point at STP, and if you remember STP, 0 degrees Celsius and 1 atmosphere, and at STP, we had a conversion factor of 22.4 liters of the gas. At STP, and at the end of your stoichiometry, you can convert away from moles. Again, you can get mass, you can get the volume of the gas at STP, or you can use the density again of a solid, liquid, or a gas to get the volume of B. And make sure you note the units too, whether it's grams per liter, grams per milliliter, or some other unit. So using that flow chart and our balanced chemical equation, and again, remember there's that implied 1 in front there. So if you need a coefficient for nitrogen, then you're going to use that 1. I want to know how many moles of hydrogen are needed to react with 6.0 moles of nitrogen. So we start with our 6.0 moles of nitrogen. That's our A up above. I'm given moles, so I'm starting with the moles. Once you start with the moles, don't go backwards. Don't go and find mass or volume or density or anything like that. You don't need to do anything else. If you're in moles, now we're ready for our mole to mole ratio. So the mole to mole ratio is going to take our, we're converting from nitrogen to hydrogen. So the hydrogen is going to be on top. So we have 3 moles of hydrogen in the numerator. And we want to eliminate nitrogen. So we're going to have the 1 mole of nitrogen in the denominator. The moles of nitrogen, the units cancel out. And we have 6 times 3 is 18. And we have 2 sig figs moles of hydrogen. Notice that the coefficients are exact. They don't have any precision difficulty, and so they don't contribute to the sig figs. 18 moles of hydrogen. 9 moles of ammonia. How many moles of hydrogen does it take to make 9 moles of ammonia? So we're going to start with our 9.00, watch our sig figs, moles of NH3. And on the right side, right side here, times, we have 3 moles of hydrogen that we're trying to calculate from the balanced equation. Divide that out by 2 moles of ammonia. And the moles of ammonia cancel out. And what do we have? 9 times 3 is 27, divided by 2 is 13.5. Excuse me. moles of ammonia. I'm sorry, moles of hydrogen. Moles of hydrogen is needed to give us, I didn't put the subscript 2 up above, H2, to give us the 9 moles of ammonia. Let's get things a little more complicated first. So now we want 4.5 grams of ammonia. So we have grams now. So we have to take the 4.5 grams of ammonia. First thing we need, and we want grams of nitrogen. So we're going from grams to grams. So if you look at our flowchart up above, we're basically staying in that first line here. Mass to moles to moles to mass. So grams of ammonia, we need the molar mass of ammonia. I'll spot you, but you should always follow. You know what? Let's just calculate molar mass of ammonia. We got 14.01 grams plus 3 times 1.008 grams. So we got 14.03 grams of ammonia per mole, grams per mole. So we're going to multiply by 1 mole of ammonia over 14.03 grams of ammonia. So the grams of ammonia cancel out. Now that we have moles of ammonia in our units, we can multiply, we can convert to moles of nitrogen. We have 1 mole of nitrogen from the balanced equation for every 2 moles of ammonia. And so now the moles of ammonia cancel out, leave us with moles of nitrogen. We want grams of nitrogen, so we're going to multiply by 2 times 14, 28.02 grams of nitrogen over 1 mole of nitrogen. The moles of nitrogen cancel out. And to 2 sig figs, that's going to give us 3.7 grams of nitrogen. Okay, I did take the molar masses out to 4 sig figs here. That's just my, I almost always do that, but you would only need 3 sig figs here to get the answer to 2 sig figs. For molar mass, always use more sig figs than what you need. It's not always going to be 3 or 4. So make sure you use more or at least as many significant figures as what you need in your calculation. Now, here's an example where I've given you the density of the nitrogen gas. So what volume of nitrogen gas is needed? So we're going to take that same 3.7 grams. So if we had ended with 3.7 grams, or if we had gotten to this point, then we would just continue with the calculation. We want to know how many liters are needed. So we're going to multiply by 1 liter over 1.25 grams. So that's the density of nitrogen. Going to multiply by the inverse density, and we get to 2 sig figs, we're going to get 3.0 liters. We don't need to worry about what the answer was to more sig figs. For nitrogen gas, if we're at STP, so this would be in number 2, not necessarily at STP. And until we get to gases, this is the only way we're going to have to give you stoichiometry problems. Stoichiometry problems using gases, not at STP. Now, at STP, remember STP, we had 1 atmosphere and basically 273 Kelvin. So we can get that from PV equals nRT in chapter 5. And we'll get that later on. But for now, let's go back. What volume of N2 gas is needed at STP? So if we go back to our original setup because we don't want to go into grams now because the STP, the conversion factor, is 22.4 liters per mole. So we have to go back to our original 4.5 grams of ammonia times 1 mole of ammonia over 14.03 grams of ammonia. Wait a minute, I'm saying 14.03. I made a mistake back here and I carried it through. And kudos to you who found it. It's not 14.03, it's 17.03. Now, the calculations are correct because I did them separately. So 17.03, and let's put that here too, 17.03 grams of ammonia. I knew something looked wrong. We still have our 1 mole of nitrogen over 2 moles of ammonia. Let's do some canceling. Grams of ammonia, moles of ammonia. Now when moles of nitrogen, now is when we're going to get that 22.4 liters per mole. So 22.4 liters of nitrogen for every 1 mole of nitrogen. Again, cancel out the nitrogen, and we should get, believe it or not, I guess 3.0 liters of nitrogen. Let's put the nitrogen up here. Always put your substances in as well. And I guess the 1.25 grams must be at STP. So you wouldn't know that, but this is the same answer, and so they must be the same. All right, so we've got 2 different ways of dealing with gases, and we've got the mass up above. Now, occasionally you will get some big numbers or some small numbers. In this case, we want to know how many kilograms of copper will be produced by this equation if we start with 3.5 kilograms of aluminum. So when we say moles and we have the mole to mole ratio, what we're really doing is using something called a gram mole. So mole is usually expressed in grams, so mole or grams per mole. So they call that a gram mole. But you can multiply, or for the molar mass, you can multiply the molar mass by 1,000 and you'll get kilograms, and that will be for a kilogram mole. So a kilogram mole is just the same molar mass in kilograms per kilogram mole. And there are many other examples, and a common one you sometimes will see on the AP chemistry test is millimoles. Millimoles is 1,000th of a mole, and so it's going to be milligrams per millimole. And that's an easy way of not having to do a conversion from kilograms to grams at the beginning, and then from grams back to kilograms at the end, as you'll see in a moment. So if we start with 3.5 kilograms, I'm going to give myself enough room to work here, of copper, what I'm going to do is I'm going to multiply that by 1 kilogram mole over, aluminum. I start with aluminum. 1 kilogram mole of aluminum divided by 27.0 kilograms of aluminum. Now, this is going to give me the same answer as if I had, or it's not going to give me exactly the same answer because it's going to be, it'll actually be 1,000 times less than if I converted to moles. But now in my mole to mole ratio, it's going to be kilogram moles to kilogram moles. I'm going to divide by the 2 kilogram moles of aluminum, and I'm going to multiply by 3 kilogram moles of copper. And we do some canceling here. Kilogram moles of aluminum cancel out. And now with the copper is going to be 63.5 kilogram moles of copper in 1 kilogram of copper try that again, kilogram of copper in 1 kilogram mole of copper. Now the kilogram moles of copper cancel out, and I have the unit I'm looking for, kilograms of copper. Now, at the beginning, so instead I could have started with grams of aluminum, and then I'd have grams of aluminum moles of aluminum, 1 mole of aluminum over 27.0 grams of aluminum. And then I'd have 3 moles of copper over 2 moles of aluminum. And then I'd have 63.5 grams of copper over 1 mole of copper. And then I wanted to go back to kilograms, so I'd multiply. Oh, I forgot to do the grams. So kilograms to grams, I'd have to take the kilograms, and I'd have to multiply, go back, kilograms of aluminum, I'd have to multiply by 1,000 grams over 1 kilogram. At the end, I'd multiply by 1 kilogram over 1,000 grams. And here's why the way using kilogram moles is better, because I don't have, I thought I chose green. Oh, there's the green. I don't have offsetting calculations at the beginning of the end. And basically, I just have what you see in the middle there with slightly different units. Either way, we get the correct answer. We should get 12.3 kilograms of copper. I believe in our homework, we have something, we want tons. So if we have tons, and a ton is just 1,000 kilograms in metric terms. So tons, you can use the unit ton mole. And then everything is expressed in tons of the material, ton moles of the material, and everything should work out. All right, so that's our foray into stoichiometry. The homework is due tomorrow as well, and I will see you then.